We continue today to discuss the properties of our electrons on diatomic layers. So we know that, and this goes without any complication, that given the ideal periodic lattice, and if at each lattice site of atom, however we call it, we define a single electronic state, in the simplest version of this story, without any degeneracy, orbital degeneracy, in a single non-degenerate orbital state. The only degeneracy which is allowed is with respect to the speed. So the energy is the same at each lattice site, assuming that there is no tunneling. And then you make the barriers between the neighbor sites penetrable, and the electron can hop moving from one side to another by using the mechanism of the quantum tunneling. Of course, as you remember from simple formula double well potential, it's very important that all the levels are in resonance with each other across the whole lattice, and the energy of the electron at each lattice site is precisely the same. This is why if you ignore the tunneling and you put electron and one electron at each potential well or lattice site, you will have a huge degeneracy. You may place it anywhere along the lattice. You can choose any particular potential well. The energy will be just the same. It's an n-fold degeneracy, when n is the number of lattice sites. And then what happens is a very simple thing. Also, we know that from the double well potential story. So once you have the degeneracy and you have a mechanism to mix up, to hybridize the states which are degenerate, but what will happen? It will be splitting of the energies. This is known in the theory as the level repulsion. Identical levels or degenerate levels tend to repel each other as long as the perturbation which mixes them up is present. Such perturbation is tunneling, and then as a result of all these things, what happens is the n-fold degenerate level of the electron localized in one of the potential wells splits into the band. And typically, epsilon of k is minus twice t. It will be cosine k a naught. In one dimension, if I have a multidimensional case, the same t, and hypercubic lattice with the same amplitude t, it will be kx a naught plus ky a naught, and so on and so on. A tight binding spectrum will be typically cosine dependence, and you have a k-dependent dispersion. And the rest is up to the chemical potential. If you prefer to work in the Grant, with the Grant canonical ensemble, then everything is under control of the chemical potential. And the value of the chemical potential will tell you what is the filling of the bag. Right? So in the single one-dimensional case, what we have, it's the band epsilon of k minus twice t cosine k a naught. This is k. This is the barrier zone. And this is the spectrum. Right? Now imagine that your chemical potential, which is the same as the Fermi energy, the chemical potential at zero temperature, which is the same as the Fermi energy, is chosen to be zero. It goes like just here. This is the case of an exact particle-Hall symmetry, when the negative energy states can be mapped onto the positive, as just said by a simple particle-Hall transformation, which we have described already, discussed. But to us it's important that if the number of electrons which is the sum of all the sigmas and all the n's, sides, speed projections, C and sigma, dagger C and sigma. Or to be more precise, perhaps I have to take the ground state average, because this is an operator. It cannot have a C value there. C values, if this number on average transforms to the number of latest sites, then you have 1 electron per site, and the band is half filled. If the band is half filled, it means that all the negative energy states are filled, all the higher positive energy states are empty, and the Fermi momenta, plus minus kF, shown here, this is kF, and this is minus kF, are equal to plus minus pi divided by 2a. So this is the band. All the states in this band are described propagating excitations, block waves. They go to infinity. If you let them go, they will go to infinity. They are not exactly precisely plane waves, because there is a periodicity of the lattice, and the wave function contains also a periodic component in the structure, right? So it's a typical metal. The Fermi surface in this one-dimensional case comprises just of 2 points, plus kF and minus kF. So you can think in terms of, say, a 3-dimensional sample. In the 3-dimensional case, your Fermi surface is a sphere, and this is the momentum k, whose length is kf, and all the points on the surface belong to the Fermi surface. This constitutes the Fermi surface. All the states inside filled, all the states out are empty. But if you now imagine that you only allow your particles to move in one direction, say in the z direction, what you do, just you build up this axis, the z-axis, and keep only 2 states, this and this, the northern pole and the southern pole. And this is precisely this point on this point. You can think of one-dimensional theory as a projection of a 3-dimensional theory on a single axis. So what was a sphere now is degenerate into 2 points. Previously you had this continuous manifold, continuous compact manifold. Now it has have a disconnected manifold comprising of 2 points, plus minus 2kF. And 2kF is the Fermi diameter, which plays a very, very important role here. So these states are degenerate by construction. The states with plus kF and minus kF are degenerate. In fact, any 2 places with k and minus k are degenerate, but to us, since we understand that in low temperature physics and low energy physics, what is important are the states close to the Fermi surface. Because of the Pauli principle, we cannot go deep inside the Fermi sphere. Everything there is occupied, so we have to stay close to the Fermi surface in a thin layer. So we have to consider the vicinity of these 2 points to make some progress.
So in this case, only this line is occupied if we talk about...
No, it's simply what I'm saying. You can imagine that you deform your lattice in such a way that you keep the hopping in z direction much, much greater than in the transverse direction. Then it's absolutely clear what will happen. Instead of this Fermi sphere, you will start getting ellipsoids, which will become thinner and thinner the greater as the center. What will remain at the end of the day, you will be left with 2 points. That's it. Yeah, you're right. So, because of this degeneracy, any perturbation which mixes up these 2 states, this and that, will tend to split these 2 points. In other words, to open up a gap just precisely at the Fermi surface because of the hybridization between these 2 points. What kind of perturbation might be? This is the clue. The perturbations whose Fourier expansion contains this component. Contains maybe, I should say, only this component, or at least this must be the greatest, the most strongest component. Just imagine you have a potential, a simple potential, scalar potential, spin-independent potential, which looks like this. I will write down delta. I will sum up over n. I will sum up over the spins, if you wish. I will put here the operator n and sigma. I remind you that this is the occupation number operator, which is C and dagger C. C and sigma dagger C and sigma. But in between, I will put -1 to the power of n. In other words, I will make this potential sign alternating. It will be, say, positive on even sides and negative on odd sides. And immediately I have a picture of 2 sublattices. On the even sublattice, I have one sign potential, and the odd sublattice, I have a different sign potential. Why it is something that I want? Because I know perfectly well that this quantity has this funny representation, well known from the ancient time of Euler, the mathematician who invented this complex analysis and these notations. Ip times n. This is exactly what -1 to the power of n is, right? Because it's a cosine, it's nothing but the cosine phi n plus I sine phi n. This is 0, so what remains is only cosine, and the cosine is just this one. For even n, it's 1, for odd n, it's -1. Right? But on the other hand, what is written here is nothing but I pi divided by A naught times n A naught, which is I, Q, and A naught. Now it looks like an exponent in the Fourier component expansion of some function of this potential. I can now look at the potential delta of n and expand it into a Fourier series like this. And if I keep only one component with Q small equal to Q large, I will immediately get this. But I can immediately identify Q as the quantity which is twice KF. This is why, if you break translational invariance and introduce a potential which makes the new symmetry corresponding to the period doubling, that immediately will mix up these 2 states and open up again. As a result, you will find an energy gap exactly at the Fermi surface, and your metal will nicely transform to an insulator. You say bye-bye to your metal, and you're insulated. That's all what happens. Very important consequence. It's the way how insulators may occur, may be developed, may be built out of the original metals. You have to introduce external perturbations, or you have to deform your lattice, you have to introduce a different chemical content to the structure, to the compound you're dealing with. And if this condition is satisfied, you'll get a transition to an insulating state. I think that during the previous lecture, we discussed, yeah, before I continue, so let us now formulate the problem. The problem is formulated quite obviously. You have a Hoppe term which describes formation of the conduction band, if there is only this term and if this condition is satisfied. I have a nicely looking half-filled conduction band. This is not all. To this I add an extra term, which is this one. It's a sign alternating, or sometimes people say staggered potential. C and sigma, delta C and sigma. Which is supposed to transform our metal to insulator. And we would like to know the properties of the insulating phase and how it different, to what extent it's different from the metallic phase. Well, obviously, insulator is an insulator. You don't have any conduction at zero temperature. The concentration of it, if you have a gap, something like this. This is the picture that you have. This is the energy, this is the momentum, this is your gap, this is your gap. And if the temperature is much less than this gap, then the concentration of the particles thermally excited from the lower band to the upper one, as well as the holes in the lower one, are exponentially small, are proportional to the exponent minus delta divided by T, and therefore all thermodynamics and all kinetics will contain the smallness. So in the limit of zero temperature, you have nothing. You're left with nothing. So this is the model which describes a diatomic lattice, one-dimensional lattice, which is built up in the following way, and so on. Somewhere here, we have the zero of the energy, or the zero of the chemical potential. This is the level whose value is delta, and this is the level whose value is minus delta. And everywhere on A sublattice, the energy is equal to delta, and B sublattice, the energy is equal to minus delta. This is the picture. Now this picture is quite helpful because it helps understand what happens in the limit when the hopping amplitude T is small. If the hopping amplitude T is much less than delta, and under the condition that Ne is equal to N, the number of electrons is exactly equal to the number of lattice sites, we can anticipate the structure of the ground state. This is what is called the atomic limit. This is what is called the semi-classical approximation, if you wish. Because we drop out kinetic energy. This is the kinetic energy. We say that, please first forget about T. Please first forget about the ability of the particles to propagate. Please look at the classical configurations. Classical in the sense that you don't allow the particles to move. You can only distribute them in such a way that the energy reaches its minimum value. If you have on average one particle per site, at the most you can put in the given site two electrons. One will spin up and the other will spin down. You can't put more because of the power bands. Right? So then if you don't have this T, if you don't have this hopping, what you do here, you put a pair of electrons here, a pair of electrons here, and you keep all the other sides belonging to the A sublattice empty. Empty sides on A sublattice, doubly occupied sides, because in this way you reach the lowest possible energy, satisfying the condition that the number of electrons is equal to the number of lattice sides. Now look what you've got. If before you started doing all these deformations and distortions of the lattice, pushing the level of the A sublattice up and the level of sublattice B down, keeping everything translation in red, and before all of that, you were sure that one thing must be guaranteed by 100%. This is the electron neutrality, which we never discuss seriously, but it's always assumed to be obeyed. The system has to be electroneutral in general. That means that the charges or the ions that form lattice sides are precisely compensated by the negative charge of the electrons which are dispersed across the lattice. Right? Some degrees of freedom may be more or less localized, but in general, everything is compensated, even locally. There is no deformation, nothing like this. But now look what happens here. If originally each side was on average neutral, here you removed the electron, which made the side neutral. So the positive charge of the ion remains on screen. So there is a positive charge plus Q here. Now what happens here, one electron already would have done the job and keep the side neutral. But you add another electron. So therefore, the charge which appears here is minus Q. Q plus Q here, minus Q here. So I have a sequence of positively and negatively charged centers. It's a typical ferroelectric. And there is a huge electric field in such a center. At the same time, you may say that it's a typical charge density wave, because charge widely fluctuates from side to side, from minus values to plus values. So it's a standing charge density wave, which does not propagate, which is stuck, which is glued to the underlying lattice, but which gives you the picture of your insulator. Your insulator is insulated because there is a charge density wave there. In metals, there can be no frozen charge density wave because they will be dissolved because of the ability of the electrons to leave their places and redistribute themselves across the whole crystal and compensate from any excessive distortions of the local distortions of the charge. This doesn't happen here. It's a different story. All right, so we understand that this is the ground state. And then I leave it to you to play a game with this configuration and try to build up elementary excitations, just in the same limit. Assume that now T is non-zero, but still much less than the gap delta, and try to build up a state or states which describe excitations. Let's try, let me give you a hint. So again, we start from this picture. This is the original picture, right? A pair of spins and nothing above, right? What you can do if you switch on this T, you can try to build up such a configuration. For instance, you keep this electron up here and bring this down electron to the neighboring side, and so far you keep all the rest exactly in the way it was before. So from the point of the ground state, here you have an excited particles on the upper level, and here you have a hole, because there were two spins compensating, two spins with the total charge minus Q, and now this side transformed to something neutral with respect to the original ground state. This is an extra perturbation, which represents a hole with a positive charge. Now the question is, can you organize things in such a way that this overturned spin here, or this absent hole, absent state, start being delocalized in higher orders in T? You understand what I'm saying? So you do now a kind of perturbation theory, if you wish. But try to understand this qualitatively without formulas. Well, the formulas are important, but try to understand qualitatively what will happen if you let this particle propagate. How is it able to propagate? Here I can immediately anticipate one obstacle, one complication. If I go back, that will be an original state. That will give me a kind of, I would say, self-energy for the particles. It doesn't go far away. It can hop up and down. In the second order, it will normalize its value of its energy, not a big deal. But this particle cannot go to the right. Please don't forget, the hopping is only between nearest neighbors. This spin cannot hop on the side because this side is already fully occupied. The Pauli principle forbids you to put the third electron here. Think about it. I nevertheless insist on saying that there is a possibility for the overture spin to propagate across the lattice. What is the mechanism? It's up to you to decide. All right? So it's for you. Maybe by Monday you will tell me what you think about it. All right? So this is the limit. T is small. The ground state is this. How do the excitations look like in such a model? How would you conclude that indeed it's a picture of an insulator? This is a typical behavior of excitations in an insulator. That's fair. All right. But that was the atomic limit. That was the limit of a strong coupling. Now instead, well, let us understand what's going on in the weak coupling limit, namely in the opposite limit. In the opposite limit, when delta is much less than T under the condition that ME is still at. This is the case which we'll be interested in. This is the case when you can start from this picture, from metallic picture, and look at delta as a weak perturbation. But it's a non-trivial perturbation because it removes the degeneracy. You should remember from the course of quantum mechanics, there is a perturbation theory for non-degenerate levels, non-degenerate states. And there is a special chapter of perturbation theory in quantum mechanics which describes perturbations for degenerate states. And all what we know about the block waves is just about that. We built up linear combinations which satisfy the block theory. But otherwise, it's a linear combination of non-perturbed states. So we will let us try to start doing this problem. Start solving this problem under this condition using the second quantization formula. I must tell you that if you look at my lecture notes, there you will find quite a familiar approach, which is the same Bogoliubov's UV transformation, but adjusted to the case of Fermi statistics. Because what we did with the UV transformation for antiferromagnets was the bosonic version of the original ingenious bosonic version of the Bogoliubov transformation, which when he was building up, perhaps from Professor Kiselov we already know that, it was building up the theory of weakly non-ideal Bose gas. That transformation was invented, designed for the first time in history. So you can do now the same, but in fact, in the Fermi case, this transformation is not only canonical, it's also a unitary. Therefore, it appears to be just simply a rotation. So I will explore the fact that this transformation is unitary, and let's take advantage of that. So you will have two derivations, the one which I will present you here now in class, and the second which is given in my lecture notes. If you know the both, or at least one of them, which is fine. So the first thing we do, we go to momentum representation. As you know, in quantum mechanics, you can choose any Hermitian operator, not necessarily the Hamiltonian. Any Hermitian operator acting in the same Hilbert space as your Hamiltonian. And you can build up the the eigenspectrum of this Hermitian operator, knowing all its eigenstates and which are orthonormal and represent a how it's called, not the full but complete set of states. And then you can expand in this basis. In other words, what I'm trying to say is the choice of the basis is up to you. Now I'm choosing block waves originally defined in the original previous zone of the undistorted lattice. This is the brilliant zone of the translation and invariant original lattice. This is the brilliant zone. And here, therefore, I write down k is less than pi divided by a naught, ck, and this exponent. I have 100% all the right to do that. I could have expanded in any other set of states. This is one of the most natural things, because when delta is small, perturbation, it's quite natural to start with the spectrum of this one. And that's exactly what suits my purposes perfectly well. Now we know that if we call this piece H dot and this piece we call H delta, then we know that H naught will transform after this transformation to the standard tight bonding Hamiltonian when epsilon of k is minus twice t and cosine k a naught. I'm considering the one-dimensional case, so it's a simplification. Now, please take into account the fact that this is the external field, which has its Fourier component, q small equal to q large, only one, which is pi, which gives rise to plus minus oscillations in real space, right? So let me once do it. If you sum over n the expression, I skip the speeds, they are not important. If you try to do it, it will be sum or 1 over n, sum over k prime, ck dagger ck prime. And now I have one summation over n. Let me write it down. I pi n. And the exponent. From here I will have minus I k n naught. And from here I will have plus I k prime n naught. So all in all I will have an exponent I k prime minus k plus pi. And if I could equally well write down minus pi, because the points plus minus pi constitute a single point. The difference between them is 2 pi, and 2 pi is just the width of the brilliant zone. Therefore, since the brilliant zone is glued, it represents a circle. Don't forget, it's not a segment, it's a circle. These 2 points are the same points. In band theory, we should keep this in mind. Yeah, so therefore I can write down, so what remains from here, 1 over n times the sum will give me delta k prime k plus q large. When q large is just pi divided by naught, that very Fourier component which characterizes this potential. And then will leave me with sum over k, ck dagger, ck plus q large. Again, leave it to you to prove. I can't hear the objection. Where is the Hermitian conjugate of this term? It's only one. I'm asking you. Maybe you will tell me. I would expect plus ck plus q dagger ck. I don't write this term. It's only this one. How can I be sure that without this term the whole expression is Hermitian?
We are summing up with k index and
you know the answer. You don't have right to speak. I know you know the answer. Who else? what shall we do? Just try to pick the Hermitian conjugate of the sum. What will you get? The Hermitian conjugate of the sum is equal to what? We have to first write down this and take conjugate, and then write down this, and again take the conjugate. Right? But this you sum over all values of k belonging to the first Brillouin zone. Is it important to choose the Brillouin zone to be located between minus pi and pi? Does anyone pushes us to keep this rule of the game? The answer is no. Any interval with the length of 2 pi with endpoints identified does the job. You can choose from 0 to 2 pi, for instance. Therefore, nothing precludes you to introduce k prime, which is k plus q, right? And then k will be k prime minus q, but k prime minus q is the same as k prime plus q, that's for sure. And the summation over k will be replaced by summation over k prime, but I don't care whether the choice of the limits, which restrict the space by the first Brillouin zone, are different. It's the same. So therefore, this expression is self-conjugate. It's already Hermitian. You don't have to add anything else. It will be quite frequently, you will see in situations like this. You must be extremely careful. Don't complicate your life, because it's enough complicated by itself. Right. Yes. So the Hamiltonian in momentum representation transforms to what? It's sum over k less than pi divided by a naught, summation over the spins, and here I will write down epsilon of k, ck sigma dagger ck sigma, and plus delta ck sigma dagger ck plus q large sigma. Now you can see immediately that the spin plays a passive role. It appears as a parameter. So you can skip it, but keep in mind you can recover the spin at the very end of calculation, and all you would need to do to multiply the whole answer by a factor of 2, taking into account 2 spin projections. So from now on I will not write the spin, but you have to keep in mind that every time I write k, this means k is supplemented by its own spin variable c. But still it's not nice, because I would like to work with the normal mode expansion. I would like to find such a representation that the new variables completely separate from each other. Like we have in lattice vibration, like we have in normal metal. We have a sum over k. For instance, for a normal metal, we would have this one. That's perfectly what I would like to have. Different k's don't talk to each other. They are completely separated. But here we have a mixture, k and k plus q. So we have therefore, why it happens like this? Why now the expression in momentum space is not diagonal? Because you have broken explicitly translation invariance. The original translation invariance was periodicity with respect to the translation in multiples of A naught. Now this is after you shifted the levels and introduced 2 sublattices A and B, the periodicity is in multiples of 2A naught. The unit cell contains two atoms. Since the unit cell contains 2 atoms, it's quite natural to expect that the true Brillouin zone will not be this. It will be just 1/2. pi divided by 2a naught minus pi divided by 2a. And let us call this interval q. Let q be the momentum which specifies this new reduced, twice reduced Brillouin zone. And now you see that if you have a ck such that your k coincides with q, that means that your k belongs to the reduced Brillouin zone. Let us call this operator ak. That every time you occur somewhere here, which means that if you have ck such that your k goes outside, then you can write down with such k. So with such k, what you can do, you can write down the following things. So ck plus q, with k belonging to the smaller interval, can be divided by dq. So this is k not belonging by the reduced Brillouin zone, something like this. And then you rewrite everything in terms of new variables. So what you do, you replace summation over k by summation over q, which goes within the smaller interval. I don't write sigma. So I take first the case when k belongs to q. K is within the new Brillouin zone. Then I have this epsilon of q, aq dagger, aq. Now the second option is when k represents a combination like this, when k is again belongs to the reduced Brillouin zone, but k plus q pushes it outside. But when you make a shift k plus q, the epsilon of k changes its sign. Because q is pi. Epsilon k plus q is minus twice t cosine k a naught plus pi. It's minus epsilon of k. So therefore, what I have here, I put this with the minus. Is it clear what I'm saying? When you want to explore the outer parts of the Brillouin zone, original Brillouin zone, we have to treat them as if they are the states inside the new Brillouin zone plus q. Because q is just the vector which pushes a state inside the new Brillouin zone to the remainder of the original Brillouin zone. This is fine. Now the second term becomes very, very simple. Why? Because if k belongs to the new Brillouin zone, in other words, if I have this one, then this operator should definitely be outside of it. So therefore it is bq. And of course, I can have the other way around. This can be the outer part, and it is bq dagger. And now I have a of q. Full stop. So with these new notations, I achieved what? I mapped the original problem defined in the old Brillouin zone onto the new Brillouin zone, twice smaller Brillouin zone, because it correctly accounts for the period doubling, for the new translational symmetry. Now I'm absolutely happy in one way. I have q everywhere the same. I have a summation over independent q's. The total Hamiltonian is the direct sum of different contributions. But if I think of this Hamiltonian as a quadratic form of A and B fields, it is still non-diagonal. So it remains to be diagonalized. How to do it? If you have any questions here. This is a very important part. You have to have a clear understanding of what I've done. Is it clear? Are you maybe not completely clear. All right. So that's the homotopy. Now we can formalize our life in a very nice and elegant way. In my opinion, this is the only right way to do, because there is no need to refer to UV transformations when they are not required. The UV transformation was invented for the situation when the space, the group space, the symmetry space is non-compact, as it is the case for bosons. Bosons are particles defined in a non-compact manifolds, always. And this is why you cannot use their canonical transformation. You can only, you cannot use their unitary transformation. You can only use their canonical transformation. Now this is just the opposite case. This is a simpler case when everything is canonical, not only canonical, but unitary as well. How to make sure? You introduce a spinor. In literature, you will frequently find the name of numbus spinor. Numbus spinor. If you go up along the stairs in this building and see the photographs of all these Fields medalists and Nobel winners, you will find this name. Number was one of the great figures in physics of high energy physics. And he was promoting the ideas of superconductivity in the particle physics. And this spinor is after him. It bears the names of Dirac and number. It's a Dirac number or number Dirac spinor, but I call it simply number spinor. So it's an object. A typical object, two-component object, just designed to work with 2x2 matrices. What are those matrices? Those matrices are Pauli matrices. Paul A takes values 1, 2, 3, or sometimes you can call them X, Y, Z. I don't want to write them down, so all what you need to know is that the product of these Pauli matrices is Kronecker here, and here the Levi-Civita, A, B, C, and those. And you know it perfectly well. This is the algebra of the tau matrices, each tau matrix. Together with the identity matrix, sometimes it's called tau knot. These four matrices form a basis of all Hermitian 2x2 matrices. Any Hermitian 2x2 matrix can be expanded in these four matrices. 3 Pauli matrices plus 1 identity matrix. And this operator well, how should I write it down? Let it be M. If I have a matrix M with the matrix elements M, I, J, and this matrix M acts on psi, what shall I do? I will write down M11, M12, M21, M22. I will write down psi 1, psi 2. This is my psi 1, and this is my psi 2 in this specific case. And then multiply it in the way we all know. This times that plus this times that. And here I have M21, psi 1 plus M22, psi 2. So I obtain again a spinor whose components, this is the psi 1 prime, psi 2 prime, are given by these combinations. In other words, I can write down psi prime I, this M, I, K, psi K, summation of K. I think I'm telling you something you already know from ancient times. It's just standard algebra, linear algebra. So where are the matrices? Now please look at this. Your Psi operator. It's an operator at the same time it's a spinor. Your spinor operator enters this expression in this combination. It gives you A dagger A minus B dagger B. What kind of combinations I may have? I may have psi dagger, some Pauli matrix TA, and again psi. And I remind you that tau 1 is 0, 1, 1, 0, tau 2 is 0 minus I, 0, and tau 3 is 1, 0, 0, minus 1. And tau naught is the identity matrix is 1, 0, 0, 1. I have to have these combinations, for sure. What kind of combination may be this expression? What do you think? It's A dagger A minus B dagger B. Look at the structure of psi. Which Pauli matrix should be here? How do you think? Oh, this must be simple. What?
Tau 1.
Loud, loud.
Tau 1.
Tau 1? Why 1? Tau 1 is off-diagonal. I'm sorry. Look at tau 1. Tau 1 is off-diagonal. It mixes A with B and B with A. So you have to look for a diagonal matrix. If it were identity matrix, then you would have a plus sign here. Since you have a minus sign, it's of course, as you correctly said afterwards, it's tau 3. So what is written here, it's nothing but psi dagger Q, tau 3, psi Q. This is what we have for this. And what we have for this? This is what you suggested in the beginning. This is a perfect tau 1. Because the sign is plus, there is no imaginary I, and this is psi Q dagger, tau 1, psi Q. Is it clear what I'm saying? I think it is. Since it's clear, then I observe that my Hamiltonian has the following structure. HQ, it's sum over Q. I don't write the spins, don't forget. Q is less than pi divided by 2, psi Q, dagger. A new Hamiltonian 2 by 2 matrix H of Q and psi of Q, where H of Q, 2 by 2 matrix is epsilon of Q times tau 3 plus delta times tau 1. Do you agree with me? You do. So what is the problem? The problem reduces to diagonalizing this matrix, H of Q, which is a 2 by 2 matrix, which can be written in the following form. It is epsilon of Q, it is minus epsilon of Q here, it is delta here, it is delta here. Full stop. That's your matrix. And you have to diagonalize. Suppose you have a limited problem. It is not the full solution, but let us do it step by step. First, you want to know the spectrum. You don't do, of course, you have to know the eigenfunctions as well. You need to know that. But let us take a restricted point of view, limited point of view. Let us first find the spectrum. How to find the spectrum? Suggestions? In the simplest, straightforward way, such that you all know this. If you have a matrix, 2 by 2 matrix, let's say Hermitian matrix, you want to know its eigenvalues. How you find it? Come on! I can't take it anymore. I will explode.
The determinant should equal to 0 after subtraction.
Which determinant? Determinant of what? Of this matrix?
Minus 1 times.
Aha! Thank you very much. That's the much better. So you have epsilon Q minus lambda minus E. delta, epsilon q, no, minus epsilon q minus e equals to 0. And the result is E is equal to plus minus, E plus minus. E plus, there are two branches. There are two branches with opposite signs. Q, Q. Then E of Q is the square root of epsilon Q squared plus delta squared. Now I want to ask you a bad question. Why there are two symmetric solutions, plus minus E, plus minus this quantity? Why there is a symmetry E to minus E? Why? Could have been it, okay, it's a result of our calculations. Could have been it anticipated. Could you expect before calculations that the spectrum must be symmetric with respect to this transformation, E to minus E? Why? Any ideas? I will wait a minute, maybe a couple of minutes, because it's a good question. I'm not warning you, I'm just telling you that doing theoretical physics is not only knowledge. It is, of course, knowledge. It is, of course, a deep knowledge. But it's mostly understanding. The more you understand before you turn to calculations, the better will be the quality of your calculations. You must understand them. If you simply rely upon your calculations, on the rational calculations under any circumstances, that eventually will devaluate all your effort. You must squeeze out as much knowledge as possible from very general considerations using minimal efforts, minimal physical efforts. Mental efforts, yes, of course. Then you will refine your skills, your technical abilities, your calculations will be fluent, it will be a pleasure to watch them. There are some calculations which look like music. So beautiful. But before you start doing that, just let your music form in your mind. Let it start sounding here. And then you will, through your fingers, through your eyes, your ears, put on the paper. So why? The spectrum must be invariant under transformation E to minus E. Okay, the hint comes from the following observation. Watch carefully at the structure. How many matrices are present here? How many Pauli matrices are present here? Two. Which is not present? Tau 2. What about the algebra, mutual algebra of Hamiltonian and Tau 2? What do they do to each other? Commute, anti-commute, what? What is the property of different Pauli matrices? Two different Pauli matrices, what? Commute or anti-commute? Anti-commute. Okay. So if you take the Pauli matrix Tau 2, then you watch that your Hamiltonian H of Q anti-commutes with Tau 2. Anti-commutes. Right? You agree? Now you have a state psi. Okay, let me put it phi. Which is an eigenstate of my Hamiltonian with some energy here. Now I built up this new state, phi tilde, which is Tau 2 phi. And now I'm acting by H on phi tilde, which is H Tau 2 phi. Anti-commute, right? Minus L2 H 5. But it's an eigenfunction. So therefore it's minus epsilon, minus energy, L2, right? And minus energy. Conclusion. For any eigenstate of this matrix, you will find another eigenstate according to this prescription, which is also an eigenstate or the same operator H, but with the opposite value of the eigenvalue, opposite value of the eigenvalue. So E goes to minus M. That's the symmetry. This is what this has to do in particle physics with charge conjugation, particle hole symmetry in condensed matter physics. You can very often anticipate the structure which is symmetric with respect to some lines have zero energy or zero chemical potential. So two bands will be present, one positive, the other necessarily negative, and which simply is inverted, the upper one. The lower is the inverted upper one. So it's important. All right. Good. So we know the spectrum. Now let us find out whether or not how the spectrum looks like. Of course, this spectrum has E of Q, say the positive branch, is square root of 4 times T squared cosine squared Q A naught plus delta squared. And this is your new Brillouin zone. This is K A naught pi by 2 minus pi by 2. This is prime. This is the old Brillouin zone. And this was the original spectrum. Minus twice T the cosine. Right? And these were your, this and this were your vertipoints. Correct? And the vertipoints would be located at pi divided by 2. At pi divided by 2, the cosine goes to 0. And therefore, epsilon of Q at Q goes to pi divided by 2, or with plus or minus sign, goes to delta. This is for positive branch. And the negative branch will give you minus delta. So what happens? This is what happens. The gap opens just at this point. So you are left with the last step. This is the picture in the old Brillouin zone. We have to bring it to the new Brillouin zone. In other words, we have to map this onto the original one. And this will be just this one. You cut off these things, and this is the picture of two band insulator. The gap. So this is the picture of a two-band insulator. Why two-band insulator? Because you can now easily calculate the number of states in the lower energy band. The lower energy band contains n divided by 2 k states. Why n divided by 2? Because the Brillouin zone is twice smaller than it was. In the original Brillouin zone, the number of allowed k states were n. With a spin, it would be 2n. But where spins are so far not taken into account, it will be n divided by 2. Now, at this very point, we switch on the spins. And we have to multiply it by 2. Right? And we get n allowed states, with spin included, for n electrons. So all electrons go to the lower band and completely fill it. And there are no more electrons left over. In other words, the upper band is empty. It's a typical example of an insulator with a finite energy gap between the conduction band and the valence band. Valence is completely filled, and the upper one is completely empty. And there is a finite gap. That's a model of an insulator. So if you want to excite such a system, what you have to do is take a state from here, take an electron from here, and bring it somewhere here, across the gap. So we'll be left over with a particle in the upper band and the hole in the lower one. And the excitation energy in both cases will be positive different. And we'll start with the excitation energy, say for a particle, excitation for a particle. It will be a gap that you need to, you have to expand this amount of energy, and if you expand a little bit, in small p, you will get p squared divided by 2m star, when m star is the effective mass, understood in the sense of band theory, which by no means should be mixed up with the mass of the bare electron in the vacuum. It's an effective mass in band theory, and you know how it looks like. Well, so this is the end of the story for the spectrum, and those of you who wanted to see how the metallic behavior is replaced by an insulating one will be quite happy with what we've done here. But we also want to calculate what is called the charge density wave. We would like to see how the charge is now redistributed across the lattice as a result of the formation of the new state. For that, we now need to know not only the spectrum of this Hamiltonian, but also its wave functions. In other words, we need to know all the details of diagonalization. We need to know that math matrix which diagonalizes this. Let's do it now. We don't do this. I repeat again that the derivation given in my lecture notes is completely equivalent to what I'm writing now, but it's slightly different in details. Essentialism. So it is one analogy which is very helpful in this instance. This is your Hamiltonian. Does it induce in your mind, in your memory, any associations, any recollections, or does it remind you of anything you already know? Or maybe you have met anything like this in some part of theoretical physics or physics in general. This construction.
Just like magnetization?
Good. Magnetization, not the magnetization, but close to that. There is no, so far we don't have any magnetization. So far, but we have something related to magnetic physics of magnetic phenomena. What is that? How does it look like? It's energy.
Applied magnetic field.
Applied magnetic field, applied to what?
Ferromagnets.
No. There is no ferromagnets. Applied, forget about Q. Q is absolute, forget it. Throw it out. We have only this. The Hamiltonian is epsilon times tau 3 plus delta times tau 3. You correctly mentioned that it has to do with some magnetic features. What kind? Now be careful. What do you mean? A magnetic field. Where is your magnetic field? How does it look like?
The tau one is the magnetic.
Okay, let me denote magnetic field by B. B is the magnetic field. Therefore, it is B times what? B is a vector. The energy is a scalar. I cannot live with B alone. This cannot be equal to this. So B must be multiplied by something. What is that? You said magnetic. Where is your magnetism? So far I can see only the external field. Where is the substance? What is the magnetism of the substance, of the material? course it's a spin 1/2. It's a Zeeman energy. It looks like a Zeeman energy for the spin 1/2. The spin 1/2 operator is, as you know, is 1/2 the Pauli matrix. That's the property of the spin 1/2 operator. It is 1/2 times the Pauli matrix. Vector. X, X, Y, Y, Z, Z. Right? Very good. So it is 1/2 of B times sigma. No one forbids me to denote the spin Pauli matrix not by sigma but by tau. The same Pauli matrix. Right. Now what turns out is that 1/2 of B, this vector, has only two components. The first component is delta, the second is epsilon, and the third component is epsilon. That's all. It's a very strange magnetic field which has only two components. It doesn't have a component in the tau 2 or y direction. It's on the plane XZ plane. Well, otherwise it's a Zeeman energy. You remember the result for the Zeeman energy? How the spectrum looks like? It's a Zeeman splitting, which is proportional to the magnetic field. What is the length of the magnetic field here? Is the modulus of B, which according to this formula is proportional to delta squared plus epsilon squared. That's exactly what we see. So what we have done, we simply considered in Q space an auxiliary problem of the spin 1/2 and wrote down the eigenspectrum of such a magnetic field, the Zeeman effect. You see how interrelated is physics. It's completely, the formalism and the understanding of the physics behind is general. It's absolutely universal, absolutely the same as it would be the case. So, how do we diagonalize such a Hamiltonian, such a Zeeman term? So we have a magnetic field B, which has two components. This is Z-axis, this is X-axis, and this is Y-axis, all right? In fact, I have to write down here tau 3, tau 1, and tau 2. And my magnetic field lies in this plane. All I need to do is to choose a new reference frame with the Z prime axis along the field, with the X prime axis rotated. This is some rotation angle theta, the same rotation angle, and with the Y-axis the same. In other words, I have to rotate around the Y-axis by some angle theta to achieve that the magnetic field loops now along the new Z-axis, Z prime axis. That's all I need. In other words, I need to perform a rotation around this action, around this axis. So this rotation can be achieved by the following thing. So it's I theta divided by 2 and tau 2. If you want Q will be here. Why I write down 2? Well, it's because I'm dealing with the so-called SU2 algebra rather than SO3. SU2, it will be a transformation of my spinor, and SO3, it will be a transformation or rotation of the bipolar matrices. So what I need to do, I have to again keep in mind this. I will suppress Q, I will consider a fold like this. And now I will say, let me consider a new spin of chi related to the original one by this transformation. This is a 2 by 2 matrix, you can see, right? How does this matrix look like? It is 1, it's a cosine of theta by 2 plus I tau 2 and sine theta by 2. Is it clear what is written here? If I look at this matrix, it will be a cosine theta by 2. Here I will have a sine theta by 2. Here I will have minus sine theta by 2. And the cosine theta by 2. Do you recognize the structure? It's a rotation matrix. It's a planar rotation matrix. Nothing special. It's a fancy way to write down something that we know. This is exactly what is written here. Right? So this is like this. So therefore, the conjugate spin order will go like this. But I know that W is a unitary transformation. So therefore, it is W minus 1. And therefore, this, what is written here, will be chi dagger H star chi when H star is W. Oh. And everyone is silent. And no one says that I made a mistake. This is a little bit better. Yes, it will be like this. Right? Now it's an old exercise. I don't know whether I told you about that or maybe I gave you a problem with it. I don't remember. The problem is sounds very clearly and simply. We have a spinor. So the spinors undergo special unitary transformations from the symmetry group SU2. Spinors 2 by 2, but they describe spin 1/2. They are subject to unitary SU2 transformation. Those special unitary transformation whose determinant is 1. Right? It is not the special unitary transformation SU2 is not the same as SO3 rotation over 3-dimensional Euclidean space. This is a bit harder to understand, but it is not precisely the same. There are differences and important differences. For instance, if you make one full rotation of a vector under the action of the so-called SO3 transformation group, the vector will come back to its original position, its original value. If you do precisely the same with a spinor, you make one full 2-pi rotation, the spinor will change its sign. And you will be obliged to make one more full rotation for the spinor to come back to its original value. So the difference. So therefore, there are single valued and double valued transformations. So therefore, there is some differences, subtle differences. They're very close, but not exactly the same. So therefore, you may ask yourself, once the spinor undergoes a transformation, unitary transformation like this, what kind of transformation do the Pauli matrices undergo? I think when we were studying Magnons, we somehow touched upon all this in some way. And the answer is the Pauli matrices just undergo usual rotations because they constitute a vector. You cannot build a vector out of a spinor. Spinor is an essentially two-component object. The Pauli matrices are matrices, 2-by-2 matrices. At the first sight, it's not quite clear how come that you can speak, to be serious when speaking of vectors in conjunction with the Pauli matrices. The point is that there are 3 Pauli matrices. You can think of a Pauli vector with 3 components, tau 1, tau 2, tau 3. Therefore, you can think in terms of the rotating of this vector. When the Pauli matrices are mixed up, and the mixture should be described by a certain SO3 rotation. That's precisely what happens. And that's precisely what we will do next time. We'll find out that for instance, under this transformation, the matrix tau 3 will go to tau 3 cosine of theta plus tau 1 sine of theta, and tau 1 will go to minus tau 3 sine of theta plus tau 1 cosine of theta. Please notice that no theta divided by theta itself. That's the point. The rotation of the Pauli matrices is characterized by angle twice as much as the angles in the SU2 transformations, for the reason I already explained to you. Now what is left to be done? You have to find out the value of this theta, the one which makes the Hamiltonian diagonal. And it's absolutely clear what it needs to be done. You have to plug this into this expression and find a block times tau 3 plus another block times tau 1. And say that the coefficient, the complicated thing, standing in front of tau 1 is equal to 0. That will define the angle. And your Hamiltonian will be only proportional to tau 3. And that will mean that diagonalization, exactly that, leading to the result you already know, but you know now more. You know this matrix, and you know this angle. Just exactly what we've done for the magnets. If you remember, antiferromagnetic magnets. It was not enough just to find out the spectrum. That would be a relatively simple problem. A much more complicated was to find all the transformations, all the coefficients, which lead to this diagonal form. So therefore, this is precisely the same as you would find in my lecture notes with UV transformation for the problem. So we will be left some last first 10-15 minutes of work on Monday to finish the stuff and calculate the charge density wave. And after that, we will turn to our very last topic. It has to do with MOT insulators and Hubbard model. Did you do? Okay, so you've got the lecture notes, right? All right. So we meet. So our exam is planned for the March the 4th. Is it correct? You don't know. You must know. You must know it much better than me. I'm the last to know the dates, actually. Yeah. I believe it must be, according to what I remember, it must be March the 4th. That you will have at least some 10 days for preparation. All right.